the meaning here, when you calculate, because for the understanding, you may have two different understanding. 24 elements, binary search. Assume that a given key appears in the array and it's between 7th element and the 20th element, inclusive. How many comparisons do we need for the average case efficiency? Here I explain the right way, understand the meaning. We know we need to draw a binary tree, right? In our notes, I give you example calculating average case efficiency for 7 elements. Remember, I drew a binary tree for 7 elements, okay? Counting, So here, you use the same way, but you need to modify, because our condition is slightly different. Here, let me draw this line segment representing this array. This array containing 24 elements. So here, let me just write from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. No. So 7, covering. So here, so there are a few more. Okay, but our coverage is from 17 to 20. All right. This part. All right. So then, here, I tell you the meaning, the way, the right way. Okay, right way. So, all right. So when you build a binary tree, okay, use all the 24 elements. Okay? Here, why I emphasize this, use all 24 elements, because some students understood in this way. Okay? Because here you say the given key appears in the array between 7 and 20th element. Then those students, they understood in this way, because based on that condition, only appears in this range, then they just use these elements to build a binary tree. Okay? Do not use that way. Okay? So here, do not just use the elements from 7 to 20 to build the binary tree. Okay? Yeah. So the reason is this simple, okay? All right, so here, the assumption here, assumption is this, okay? Although we say assumption, all right, assumption, so here, that means it could happen, this property, so because this is a property, okay? This is a property. property of the data. Property of the data, okay? Yeah. But even if the data has this property, but this property is hidden. The property is hidden. So that means nobody tells you this property, okay? Yeah. It happens, this property happens, but you cannot, in your program, you cannot assume that, right? In your program, because you do not know this property, okay? So when you write your binary search, you cannot assume this property, right? Because the data, there is a hidden property, okay? So here, our assumption is the coming data. So you work on special collection of data. That data has certain property, but that property you do not know, okay? Yeah. You do not know, so you cannot integrate that property in your coding, right? Because here, you need to modify your code. If you only cover elements from 7 to 12, then in your code, you need to, when you pass the data, you need to specify you only cut off. You take the subarray from elements 7 through 20, you build a binary tree. You need to do that in your code, but here, as a hidden property, you do not know that, right? You do not know that property. So nobody tells you that, okay? But that property happens at the runtime, okay? So let's imagine in this way. So your binary tree, you have to use the whole original data. Yeah, the 24 elements, all the data, all the data. Yeah. So the key has that hidden property, but you cannot assume that. Okay? You cannot assume that hidden property because you do not know it. Nobody knows it. Okay? Yeah. Yeah. It just happens. At the end, if people do statistics, it happens in that way. All right? It happens in that way. Yeah. So here, in the real world situation, we should consider in that, that way. Yeah. Otherwise, so you just remove part of the data, right? Yeah. You remove, a few elements from the left, a few elements from the right. Yeah. But if you need to process different collections of data, so then this property is gone, right? New property, you may have different property, right? Yeah, yeah. So you cannot assume. Yeah. You cannot assume any property. Yeah. But so my question is just as a hidden fact. Yeah. This property occurs as a hidden fact. Then our answer is this average. Okay? Yeah. So that's the right way. Yeah. Yeah. For you, when you build a binary tree, just use all 24 elements to build. Yeah. Then, each element, you look at how many comparisons, each level, how many nodes, then you take average. Yeah. Question. Oh, yeah. Median, right? Left median, yeah. So, yeah, 24, you're right. 24, the median, yeah. So for this class, we always use left median, okay? Yeah. So always, right, let me write down here, okay? Always use the left median to build your binary tree. Okay? Yeah, yeah. Yeah. All right, so that's our, convention. Yeah. Although, if you use the right median, I believe you get same answer, right? Yeah. Right. Oh, yeah. Yeah. Yeah, could be. Yeah. May not be the correct, may not be the same answer. Yeah, you're right. Yeah. Slightly different. Because our data is not symmetric, right? Yeah. Our data not symmetric. If the data is symmetric, then you get the same answer. Symmetric with respect left and the right. Yeah. Yes. Yeah. 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 So here we use the left. Yeah. But if some students use the right median, so I won't treat as wrong, right? I mean, just different from our conventional way. Yeah. I won't treat as wrong. You know, but you know, if possible, we just use the left median. Yes. All right. Yeah. So that's this question. Okay? Yeah. Because I noticed some students ask me this question, so I want to clarify it. Yeah. Yeah. And a few of my old students actually did this way. Yeah. So that's the reason. Yeah. Some students, you know, a few semesters, so they did it in a wrong way. Okay, they did it wrong way. Yeah. So I think many students may get a wrong understanding. Yeah. All right, so that's this question. Then we need to go back to our this one. Yeah, yeah, here. Okay, right. So we are here. Yeah. So first, yeah. So we're on this slide. First, we need to complete this slide. Then, if we have more time, so I don't know. So let me see if I can use half an hour to complete. If we have a little more time, I want to do a few questions that I talked about before. You know, one question, remember, I gave you a formula, but I didn't explain. Yeah. Sorting, about sorting. Minimum number of comparisons to sort an array with n elements. That factorial, n factorial, seeding function, n factorial. That formula. Yeah, 5, right. But it's correct for all n, okay? That formula is correct for all n. Yeah. So if today I have 15 minutes, I will explain that formula, why it is correct for all n. Yeah. Not just for 5, 5, 6, 7, all n numbers. Yeah. So that idea is very interesting, yeah. Useful, not very complicated. You can understand, you know, easily. All right. Yeah. Let me run the slideshow here. Yeah, we are here. Now we know, so let me recall our story a little bit. Yeah. Refresh your memory. Yeah. Remember last time I talked about one special search algorithm called index search. Okay? Index search, on our textbook, it's called direct addressing. Okay, that method. Yeah. And we know that method is very fast because it has big O of 1 efficiency. Yeah. But it has a big problem. It uses too much memory space. Here, I want to use a simple example to explain why that idea does not work. So we have to modify it. Yeah. All right, let me give you this example. Long keys. We need to store our data with long keys. All right, SSN or student number. Yeah. So here, I just use the, typical class. Students in a class. We want to store the information for those students in a class. Okay? All right. So if we use their ID, so we have long keys, many digits, to store students. Assume 40 students in this class. Okay? 40 students. All right. 40 students. Yeah. Any question? Oh, okay. Yeah, it's fine. Yeah. All right. Here you can see it's not a good idea if we just use, if we treat the keys as the integer, if we just use the keys as the indices of an array, think about how large is the array you want to create. Okay? Yeah. Billions of elements, right? Yeah. At least hundreds of millions of elements. Okay? Hundreds of millions of elements. Yeah, because this many digits, if you want to create an array that you can access elements with indices. Yeah. So remember, because direct addressing, that means we use these numbers as indices. Indices, that means you need to create an array large enough that the elements using these big numbers as indices, you can store in your array. That meaning. Okay? Yeah. So definitely it's not efficient. Yeah. It's not efficient. Only 40 students, but you use hundreds of millions of storage locations. Yeah. Yeah. That's the reason this algorithm is useless in the real world. Okay, yeah. All right. But, although this algorithm is useless, but there is some useful idea we can explore it to build a new data structure and a searching algorithm. Yeah. So we can build our better, useful, more efficient search algorithm from this better one. This is a better one. But we can fix its problem. Yeah. Wasting too much memory locations, can we fix this problem? So the question is, can we make the memory usage better, more efficient? Do not waste that large amount of memory resource. So the question is, how do we improve the memory usage? We use simple ideas to improve. We don't need a very complicated method. Some simple way to improve the memory usage. Here, let me tell you the idea. All right. We cannot use keys as indices directly. All right. The question, how to make keys shorter? If keys are shorter, then we do not waste that much memory resource, right? Yeah. The question is, can we make long keys shorter? If it's shorter, then we use those keys, to define an array not that big to hold these 40 students. Then we won't waste a lot of memory space. Okay, yeah. So the question, make keys shorter. Okay? So we need to find the right way to make keys shorter. Yeah. All right. Yeah. All right. How to map keys to slots? Yeah. Because when we store our data, use many slots. We don't want to use too many slots. Okay? The number of slots are slightly greater than the number of students. That's okay. Yeah. A little more. We allow some extra room. A little larger than the number of students. That's fine. Yeah. But not, too much bigger. Yeah. Yeah. So we want to map keys to slots. And the number of slots just not too much greater than the number of data elements. Yeah. So that idea. All right. Mapping strategy. When we do mapping, so input is your key. Your search key is the input. Output is the shorter indexes. Yeah, locations for your data elements, yeah, but much shorter. Yeah, yeah. Long key, so input of the function. So suppose you have a function. Input of the function, the output of the function, much shorter. That idea. So that's what we call a mapping strategy. You need to, find some smart mapping strategy to solve the problem. Okay, all right. What is a good mapping? Here. So we want to find a good mapping. Yeah. Okay, all right. So here we need, these properties in our design. So here it's a, function design. Yeah. So we will call hash function. Later we will call it, we need a hash function. So now we are designing our hash function. We're designing our hash function. First, fast calculation. Yeah. When you enter the input long key, we need to do calculation. But we want that calculation very fast. Yeah. Otherwise, it's too slow. Yeah. So your search algorithm will be very slow. Yeah. So fast algorithm. Second property, evenly distributed among all the slots. Yeah. Yeah. Suppose you have certain number of slots. Okay, so that's all your slots you can use to store the data, all the slots. Okay, but if your mapping is not that evenly distributed, for some slot, too many mapping here, okay, too many mapping somewhere, but in other places, no mapping. In that way, it's a bad mapping. If evenly distributed, very close to evenly distributed, then it's a good mapping. Yeah. So the second property. Okay. The third property, not sensitive to any pattern. Not sensitive to any pattern. Because your data may have some pattern. The data may not be completely random, right? If it's random, so then, you cannot see any specific pattern. Okay? The randomly distributed. Okay? But sometimes in your data, the keys of your data, you may follow some specific pattern. If that special pattern occurs, it may break your mapping function. Yeah. So your performance of the mapping function could be very poor. Poor means, some slot you map too many elements, okay? So, some slots you map too many elements. other slots, no elements mapping, then the performance will be very slow. Okay? Yeah. All right. So here, the design strategy. Yeah. So we need to, try to consider these three aspects. Yeah. All right. Implementation. Yeah. So let's look at a simple implementation. Choose appropriate math functions. Yeah. Just find some convenient math functions. Yeah. So there are some ideas, several ideas to design the hash functions. The first one, C.2 hash functions, division method. Very simple division method. May not be very good. So later we will see. So this method actually is not very good. So we can find other better method to improve it. But this is the first one, division method. All right, so look at the idea. Hash function design, division method. Okay. Assume that all keys are natural numbers. Yeah. So our, initially, we make this assumption for convenience. Yeah. Because later we can remove this assumption. Later, if the keys are string values, no problem, right? String values, because string values, we can convert it to integers easily, right? Yeah. So we don't worry about that, okay? If we can, design hash functions for integers, so then we can cover, all keys. Yeah, all keys. We just do conversion, okay? Yeah. All right. Non-natural number keys can be converted to natural numbers. All right, so here we assume there are m slots. Slot number, m. Yeah. Element number, slot number, two different numbers. Yeah. How to map a relatively large key k to one of the slots. Yeah. So simple, fast math function to do the mapping. Yeah. All right. The first method, modular. This simple, right? Yeah. Hash function h. Yeah. So that's our hash function. H of k, its value, we just want to k mod m. Number of slots. The remainder. So you do integer division. Why we call it division method? Because you do integer division. And you only take the remainder part. Okay? So you throw away the quotient part. So you get a small number, right? Yeah. That number is smaller than slot number m. Yeah. So you can find the location in your storage table. It's a table. Yeah. M slots, we call that table. It's the hash table. Okay. So those m slots, so they form a hash table. Okay. This hash function. All right. Do that mapping. I think you can easily see this mapping method may not be very good, right? Although it's simple, fast, yeah. But, too simple, Yeah. That means it is not robust, right? You can break it easily, right? You can break it easily. Break it, that means you can make this search method perform really slow easily, okay? With some special keys, you can make it work very slow. So that's the main problem. All right. Easy to calculate, evenly distributed, no. Yeah, so you cannot, because this way, if your data has some special pattern, it may not be evenly distributed. Okay? Yeah, it depends on the keys. Yeah. If your keys are random, probably evenly distributed, right? Yeah. But not completely random. Yeah. So your key caught by any pattern. So here, you may use some special pattern to break it, to make it very slow. Yeah. All right. So here, let me use a simple example. to show you the main problem of this method. Make hash function robust. Yeah. So we want to improve our hash function. Yeah. In the division method with m slots, yeah. Example 1, yeah. Let us consider m equals 15. Okay? Suppose we have 15 slots to hold our data, hash table, 15 slots. If we do the modular operation, that simple hash function like this, then it won't be good if your data, the keys of your data has the pattern here. I choose a simple pattern here. What's the pattern? K is a multiple of 3. That's the pattern. Okay? Yeah. So the keys of our data happen to be multiple of 3. Those pattern, and this special pattern. Okay? Then h of k is also multiple of 3, right? Yeah. Because you want 15. 15 is a multiple of 3. Okay? So you use a number that is multiple of 3 to mod 15. The remainder is also multiple of 3, right? Multiple of 3 minus multiple of 3, you also get multiple of 3. So that your hash value, h of k, always multiple of 3. Then look at what would happen if your h of k always multiple of 3. Yeah. Because here, based on our modular operation, h of k minus k must be multiple of 15. Yeah? Yeah, modular, because the quotient, quotient number times 15 plus remainder, right, equals original k. Yeah. All right. So h of k equals 15n minus k, but k is a multiple of 3. Yeah. So this number is a multiple of 3. Okay? All right. Yeah. If it's a multiple of 3, then only 1/3 of the slots are used, right? Yeah. Only the slot number that are multiple of 3 are used. Yeah. Slot 3, slot 6, slot 9, slot 12, slot 15, those slots are used. The remaining 2/3 of the slot are never used, right? That's not efficient. So you waste 2/3 of your storage resource. That's not efficient. We want to use, most of it. Close to, at least 80-something, 90-something. We want to use that high percentage. Yeah. Not just 1/3. Yeah. Okay? Waste too much. Yeah. So this method is bad. Okay? For a pattern, multiple 3 pattern, that. Very bad. Okay? All right. Make hash functions robust. Yeah. Second, in a division method with m slots, the second one, if m is power of 2. Yeah. Power of 2. Yeah. So you have that many slots. Then your division method won't be good, because when you do modular operation, you just do truncation, right? Yeah. Yeah. Because you do division by 2 to the rth power, you just drop the bits higher than the last r bits, right? You do truncation. You only keep the last r bits. Yeah. Then think about if 2 keys with the same last few bits, there you map to the same location. So that's not good. If you just do truncation, then so your hash function is not robust. Okay? So you have to modify it. Yeah. Yeah. Here are just 2 simple examples. So you want to make your hash function design very robust. Okay? Yeah. All right, so here, improvement. Yeah. Here, 2 keys, same last, yeah. improvement, a good choice for division method. So here we, if you really want to choose, actually this method won't be good. So later we will use a better one. Multiplication method will be better. So we do multiplication. We don't do division. But when we do multiplication, we need to choose some special factors. So we want to, use some randomization method to break the patterns. Randomization, still, some randomization idea, but it's different from our older randomization idea. Here, we use, math operations. We use some special numbers. When we do multiplication, we break the pattern. So basically, we break the pattern. Okay, all right. So the good choice for division method, a prime number that is not too close to the power of n. So here, this method, this idea, improvement idea, basically just to fix the problems we saw in the previous two examples. All right. First, 15, we know 15 is multiple of 3, multiple of 5. That's the reason it is caught by some pattern. So the first idea, we just pick a prime number. We know prime can never be any multiple of number other than 1 and itself, right? So other than 1, it's not a problem. Itself, Then no other proper factor. So we call proper factor, okay, for the prime. Okay? So prime number is a good candidate. But another factor we need to consider, because if it's too close to power of 2, then the second problem, right? So that, truncation, similar. So for the second one, so we don't want to make it too close to power of 2. Okay? So then, when we do modulation operation there, so we won't get that, truncation problem. That problem. Okay? All right. So this way, so it can improve your division method, the performance. A lot. Although still very limited. The improvement still very limited. Okay? All right. But at least, this simple method, I believe it can cover probably 90% of the data. Okay? Because if you want to break, if we choose the, hash function like this, if we want to break it, you need to really, do some hard work, right? Yes. It's possible to break it. But not that easy. Not that easy to break it. Okay? But next time I show you the multiplication method, then much stronger than this one. Okay? Much stronger than this one. Here, still a lot of limitation. Because, for example, think about this. Sometimes, because too limited. The number of slots when I choose, limited by this one, because for some applications, I really want to use 15 slots. Okay? Because my resource is very limited. I have to use 15 slots. But I want to do a good mapping on 15 slots. Good mapping. On those 15 slots, my hash function can still do well on 15 slots, right? That's much better than this way. Our multiplication method can achieve that. Multiplication method, it doesn't matter how many slots you use. Okay? Any number. Okay? Power of 2, no problem. Power of 2, because we have some multiplication factor, even power of 2, we can, break the, randomize, make the key mapping distribution to the random locations. Multiplication. Yeah. Yeah. Here, think about pi. Okay? Pi. So when you have pi, the digits, so that's pretty much random, right? Yeah. When you have E, when you have golden ratio, right? The digits after the decimal are pretty much random. Can you use that kind of property, to make your hash function, randomly distribute, all the elements? Yeah. That's a simple idea. Okay, that's the multiplication method. Okay, yeah. Some bad number actually useful, right? Those, you cannot see any pattern, right? Pi, E, what's the pattern? Can you see any pattern? Yeah. No pattern is a good thing, right? Yeah. Because we can use it to break any pattern. Okay? Yeah. All right. Yeah, so it is expected to be robust against any pattern. Yeah. Although, its power is still limited, okay? Yeah. Empirical, yeah. So, cannot be proved, yeah. It is possible to create a special pattern to make it perform poorly. Yeah. It's possible, yeah. But that chance is not too high, not very high, okay? Yeah. Reasonable, we can assume the chance, probability less than 10%, okay? Less than 10%. But, multiplication method would perform much better. Yeah. So we can say 99 something percent. It will do well. 99 something percent. Yeah. We have that confidence, that high confidence. Yeah. Okay. All right. Yeah. So next. All right. Yeah. Probability is small. All right. Next, now, before, and I gave you the formula before, and we did a few questions, but I didn't explain why that formula is correct. Yeah. So here I need to explain how to derive that formula. Yeah. All right. So here, look at, we want to find lower bound for comparison-based sorts. Yeah. So from the name, you can see we only consider those sorting algorithms that use comparisons to determine the sorting orders. Yeah. Here you may ask, does that mean there are some sorts not comparison-based? Yes. Yeah. There are some sorts not comparison-based. Yeah. All right. So here, first, I give you the formula. Yeah. The lower bound formula, yeah, I give you before. Yeah. So here, let me give you another time. Log base 2 of n factorial. Yeah. Right. If you do not require comparison-based, you can use any method to do the sorting. Then you may have other different sorting algorithms. Yeah. So here, let me give you one special example. Yeah. This semester, we may not have time to cover this one. So this week, the last two next week, last two classes of the semester. So I don't know if so it's very likely I may not have time to talk about that. Yeah. So here, there is another sort. We call a counting sort. This one is not comparison-based. Yeah. We do not use any comparison in this sort. You can see the main operation we use, counting. We just count number of elements. Yeah. That operation we do not need to do comparison, right? Do counting. Okay? Yeah. But this is another general purpose sorting algorithm. Comparison based. Yeah. So usually we treat this type of algorithm the general purpose. General purpose algorithm. Okay? But counting sort, not general, special. Yeah. It means there are some special requirements you need to use. Okay? Yeah. So the sorts you need to assume some special requirements, special conditions. Okay? Yeah. Otherwise, you cannot apply this sorting algorithm. Okay? So what are those special algorithms? First, you must apply on integers, okay? Yeah, so not floating point numbers, only on integers. Floating point, not floating point numbers. For comparison based, we do not require that, right? So you can see how special it is. Yeah. So you may ask why integers? Because when the elements in an array are integers, then you can do the counting, right? How many elements have value 1, how many value 2, and so on, right? But if floating point numbers, it's hard to do the counting, yeah, not efficient. Yeah. For example, you have floating point number 1.3578. You know, when you do counting, it could be very messy. Yeah. So it's yeah. In general, you cannot apply the counting operation here. Okay. So that's the first assumption. Second, range assumption. The range cannot be very large. Okay, range of the values must be relatively small. Okay, yeah. So this assumption, the main reason we need a second assumption is if the range is relatively large, the performance would be much slower. Okay, so then the counting does not help. If the range is large, we would rather do comparison, right? Yeah. So the reason we want to restrict the range relatively small, because we want to get better performance than the general purpose sorting algorithms. So the range assumption. Okay? Yeah. Yeah. So, all right. So that's the special sort. Yeah. Yeah. But here I only want to talk about comparison-based sorts. Okay. All right. Yeah. So next, let's do some analysis. Why the lower bound is, so here our goal. I want to show the lower bound. Okay, yeah. Of the comparison sorts. Is this formula. Okay, and actually this formula is a very good estimate. Very good estimate. Okay, all right, so let me explain. how to derive this. Yeah. Because the method is quite useful. The method is called decision tree method. So method we apply here is interesting, useful analysis approximation method called decision tree method. Let me explain this method here. Yeah. Very interesting, very useful. Okay. So what is a decision tree? So here, let's consider a typical comparison. When we look at a comparison, how many different outcomes do we have in general? Okay, yeah. When you do comparisons, how many different outcomes? Yeah. So comparison between two elements, A and B, right? So one, you have A less than B. One, you have A equals B. And the third one, you have A greater than B, right? It looks like there are three different outcomes. But we want to combine the first two as A less than equal to B, because after this combination, we can get two outcomes. If we just make two outcomes, then we can use binary tree representation. Okay, yeah. So here, these two outcomes would give us a binary tree representation. Okay, so that would be very convenient. Okay, yeah, binary tree. So we are familiar with binary tree, right? Yeah. So we like to use simple binary tree to represent comparisons, all the comparisons in the sort. Okay, all right. So now let's look at the typical comparison representation in a binary tree. Okay, all right. So here, let's look at a comparison in a binary tree. Here we use this binary tree to model. I use this word, model the comparisons. Okay, model the comparisons. Yeah. All right. Yeah, let me use comparison between A and B. I use this notation, A colon B. Yes. So this is the node, A colon B. It means we do comparison between A element and the B element. Then we have two different outcomes we need to represent in this binary tree. All right, so one, the left branch node corresponds to A less than or equal to B. Okay, the right branch node equals to A greater than B. Okay, all right, and after that we can do further comparisons. Okay, yeah, another comparison, and here another comparison. Okay, yeah, all right. So then, with this basic structure representation, yeah, so we want to use this way. So we can draw a binary tree. So that binary tree we call a decision tree. Okay, so we can draw, because when we do comparison, we just make decisions, right? Yeah. So go where to go. You go to the left branch or right branch, which decision you make. So we call it decision tree. So draw a decision tree for any sort. We can draw a decision tree for any sort. Okay? All right. Yeah. So next, let me do a simple example to show you, in order to help you understand. How can we draw a decision tree for a sort? Yeah. So let me show you. Then we can do the discussion. Yeah. All right. Here I use a simple example. Okay? Yeah. Example. So what's that example? Sort a 3-element array. Yeah. So it's a simple example, right? Yeah. Everyone knows how to do it. Yeah. But here, I just give you the idea how people draw a decision tree corresponding to a particular sort. Yeah. Here we represent this array ABC, these 3 elements. Okay, so we use these ABC elements to draw this decision tree. Yeah. All right, so very simple. Yeah. Yeah. So when we start, we put the root of the binary tree, the decision tree, our first comparison. Yeah. So what's our first comparison? A colon B. A colon B, B, that's our first top root node. Okay? Yeah. Only 2 outcomes, A less than or equal to B and A greater than B. Yeah. All right. Then the left child node, when A less than or equal to B, what is our next comparison? Here. Okay, yeah. So although you have several choices, right? But you need to pick one. Yeah. So here I pick B and C. How about that? So my next comparison should be B colon C. Right? Yeah. So then 2 possible outcomes, B less than or equal to C and B greater than C. Yeah. Okay? Yeah. But when B less than or equal to C, we get this array sorted. Because we know the explicit order after these 2 comparisons. Right? So now our node won't be any comparison node. Our node must be the outcome node. Okay? Sorting result node. Yeah. So we use a rectangular box to represent the sorting result. A less than or equal to B less than or equal to C. Yeah. So that's the bottom leaf node. Yeah. We reach the bottom. It's a leaf node. Okay, sorting result. Yeah. All right, but here, this side, B greater than C, it's not enough to get the array sorted. We need one more comparison. That comparison must be between A and C. Yeah. So we need to do a comparison A colon C. Okay, all right. So then left branch A less than or equal to C and the right branch A greater than C. Yeah. Now we can write the sorting result nodes, rectangular box node. Yeah. All right. So this one, sorting result, okay, A less than equal to C, strictly less than B, right? Yeah. And here, C is the smallest, C less than A, less than less than B, right? Yeah? Or less than or equal to B. To write it more accurately. All right, yeah. But this is one side of the sorting results. 3 possible sorting nodes, right? The other side, this side, right branch, similar. Okay? Yeah. Yeah. You know, you use the same way you can produce the right subtree. Yeah, right subtree. Yeah. So similar. Okay? So here I do not, draw it. Yeah. Similar structure to save some space. Yeah. Yeah, because I need, quite some space to discuss our next step, derive the lower bound. Yeah. All right, so now, after this simple example, you can understand how people draw a decision tree for any given comparison-based sort, yeah, in the straightforward way. Yeah. All right, so now we need to do the same thing. This time, we do this on that general, abstract, sorting n-element array. So this time, okay, all right. So the general problem, okay, sort an n-element array. All right, so that problem, okay, all right. And this time, now, we have to explore some properties. Because if you try to draw decision tree, so only partially, it won't be easy. Yeah. So we have to, discover some main properties of its decision tree here. Yeah. All right. So let's look at it this way. All right. First, we know for any such sort. Yeah. So here we're talking about any comparison-based sort that can solve this problem. Okay. Yeah. So there is a decision tree for it. So we just discuss the common properties for a typical such sort. All right. So there is a root node. Okay. Many comparisons. Okay, going down. Yeah. Certain level. Some sorting outcomes. And so on. Okay. All right. So some. Quite generous structure. Yeah. Yeah. All right. Now, our discussion here. Yeah. The first discussion. First, we need to estimate. Okay. How many leaves? Estimate how many leaves in the decision tree. Okay? Yeah. So how many different sorting results? How many different sorting results? Can you imagine that? Yeah. Because given n elements, so you can imagine x1, x2, and so on. Okay? xn, and so on. All right? Each sorting order corresponds to a permutation of these n elements, right? So you know the permutation concept, right? So each sorting result corresponds to a permutation. Yeah, so the permutation concept from your discrete math. Okay? All right. So how many permutations do you have with n different elements? Here we assume these n elements are distinct values. Yeah. So the answer is n factorial. Okay, all right. So that means here estimated how many leaves. The answer is greater or equal to n factorial. Greater or equal to. Yeah. So you may ask me why greater or equal to, not exactly equal to n factorial. Because remember here we are talking about a general algorithm, right? Yeah. So here we're talking about a general comparison-based sorting algorithm. A general sorting algorithm means any algorithm you just get n element array sorted, right? Yeah. If an element that can get n element array sorted, it's not necessarily optimal, right? Yeah. It could be optimal and it could be non-optimal, right? Yeah. If it's not optimal, that means this algorithm may do some redundant work. This algorithm may do redundant work, redundant comparison, redundant comparisons. That's possible, right? Yeah. Redundant comparisons, okay? Yeah. So if it's redundant comparisons, then when you count the number of leaves, some of the sorting result could appear more than once. Yeah, but yeah, because redundant. So redundant more than once. Yeah. So if you have redundancy, then the number of leaves would be greater than n factorial. Okay? Yeah. Only when you do not have the redundancy. Okay? Only when you do not have the redundancy, then the number of leaves equals n factorial. Okay. So here, so we should use this greater or equal to sign. Yeah. So that's one. The next one. Next important property we observe. So that is the worst case. Yeah. Because when we estimate the lower bound, we should look at the worst case efficiency, right? So when we look at the worst case efficiency, okay, worst case efficiency, it corresponds to, yeah? How do you represent worst case efficiency in the decision tree? In the decision tree, corresponds to the height. Binary tree has a height, right? Corresponds to the height. The height. The tree has a height. Okay? Height. So here we use h to represent that. The tree height. So here it's the tree height. Okay? Yeah. It's not the node height. Yeah. In our heap sort discussion, we look at the height of a node. Here, the concept here is height of a tree. So that's different. Height of a tree, we use height of the root node for the height of the tree. So this height means height of the tree. Height of the tree, okay? Yeah. Yeah. Not height of one particular node. In our heap sort, we consider height of a node inside the heap. Yeah. So try to separate the concepts. So here, height of the whole tree, so we look at from the root, okay? So our starting point is at the root. Then we want to find a path, follow a path, reach the bottom, reach a leaf node, and that path must be the longest path. We want to find a longest path. We know some paths are shorter, some paths are longer, but we consider the longest path. How do you define longest? We count the number of edges. Edge 1, so we count 1. Edge 2, we count 2. You know, when you move along a path down, you count how many edges do you have. That number we use to measure the height. Okay, the number of edges. So here, for example, let's look at the length of this path. 1 edge, 2 edge, 3 edge. So this path has length. Yeah, so I use length. Length equals 3. Okay, this one 1 edge, 2 edge, we reach the leaf node. So this length equals 2. Okay? Yeah. But when we use the height, we use the longest one. We use the 3. We do not use 2. Okay? Yeah. So that's the height. Now, the worst case efficiency corresponds the height of the tree. Okay? All right. Yeah. So another representation. Yeah. Next one, we want to estimate the relationship between, so here, L, we use L to represent number of leaves. Okay? Of leaves. Okay? L. Okay? Capital L. Yeah. The number of leaves. And we know, based on our analysis above, we know L greater or equal to n factorial. Okay? Due to redundancy. Okay? The nodes, redundant nodes. Okay? All right. Yeah. All right, so now, what's the relationship between capital L and H? What's the relationship? So we compare with, we want to find a relationship between L and H. Okay? So what's that relationship between capital L and capital H? Yeah. All right. So here, we need to do imagination. Yeah. So to get this relationship, we need to do some imagination here. Okay? Yeah. So what kind of imagination? Yeah. All right. So think about, given the height of a decision tree. Yeah. So here, first we fix height h. Yeah. So we fix. When you do consideration, we fix that height h. Okay. So you draw a binary tree with height h. Yeah. So you fix it. Okay. All right. Then you consider, because with the same height h, you can get many different binary trees, right? Yeah, you have many different ways to draw a binary tree with the same height h. Okay, all right. Now you think about which binary tree with height h gives you the largest number leaf nodes. Can you answer this question? Yeah. So you have so many different binary trees with the same height. Which one would give you the largest number of leaf nodes? Okay? Imagine. Can you, in your mind, can you envision a picture? So the binary tree with the maximum number of leaf nodes. Okay? Yeah. So you try to expand. You try to expand your branches to cover as many ground as as many leaf nodes as possible. Okay, yeah, cover the ground, the tree. Okay, upside down. So that tree you want to cover, as much ground as possible, right? Yeah. So imagine that. Okay, yeah. So the answer is complete binary tree. Okay, so when you get because the complete binary tree, you only have one case for the complete binary tree, right? So let's use the complete binary tree. Okay? Yeah. When you get a complete binary tree, you have the maximum number of leaf nodes. Yeah. But for a given height h with complete, a complete binary tree with height h, yeah, how many leaf nodes? How many leaf nodes? Yeah. 2 to the n. Yeah, so it's a power of 2. Yeah, first the power of 2. Yeah. Power of 2. Yeah, so if you count from root, because at the root, if the root already touched the ground, yeah, if the root is a leaf, yeah. If the root is a leaf, then you have 1, 2 to the 0, right? Yeah, 2 to the 0. Then you have one more level, 2 to the first. Another level, 2 to the second. 2 to the second, height equals 2, and so on. Okay? So 2 to the h, when the height equals h, the number of leaves 2 to the h. Okay? Yeah, but that is for the maximum number of leaf nodes, right? Yeah, maximum number that should be greater or equal to the general L, right? Yeah, because the L number, capital L, is the general number, not necessarily the maximum. Okay? Yeah. So that's the L. So 2 to the h should be greater or equal to L. And another inequality we derived before, n factorial. Okay? Now let's skip this L part. So we get 2 to the h greater or equal to n factorial. Right? Yep. All right. Yeah. N factorial. All right? Then we take log base 2 both sides. After that, we take log base 2 both sides. Yeah, let me use space here. So we get h greater or equal to log base 2 n factorial, right? Yeah. H integer, log base 2 n factorial may not be integer, but we want to make this greater or equal to sign always true. Can we assume h should be greater or equal to the ceiling function of log base 2 of n factorial? Not floor function, ceiling function. Yeah. Floor function, so you may not cover, sometimes you may not cover. Okay? Yeah. So when you use the ceiling function, then it's always true, right? If h greater or equal to the ceiling function of log base 2 of n factorial, then thus you guarantee this inequality always true. Yeah. If you use the floor function, you cannot guarantee the bottom inequality always true, right? So for that reason, our best estimate for the worst case, here we estimate the worst case, is the ceiling function of log base 2 n factorial. How about that? Okay? So that's the whole derivation process. Okay? Yeah. The lower bound formula for comparison-based algorithm. Okay? Yeah. So try to understand. Yeah. Here I use this example, I want to teach you how to use the decision tree method to do analysis. Yeah. So in some special situations, it is very useful. Okay. All right, so let me finish this topic. Yeah.